Yeah, thank you very much for the introduction, and thanks to the organizers for giving me the opportunity to tell you about this. So, that way. The general question is, if we have a system of diagonal equations, we've got some here with each equation is homogeneous, but we may have a range of different degrees. We can have degrees that occur often, others that don't occur at all. So what's the number of integral solutions to systems of this kind? Well, let's start by thinking about what we expect. Trivially, well, the number of possible inputs is the number of variables, gives you p to the s. The number of possible outputs, each equation takes p to the ki values up to a constant. So if all of them are supposed to take a certain value at the same time, we would divide by p to the total degree. Of course, this assumes some kind of independence. So we'll need some kind of non-singularity condition on the coefficients there, because otherwise, well, we could have twice the same equation, right? So we need to avoid things like that. And there may be other good reasons why we might not have any solutions at all. For instance, if we have definite equations in there, say a quadratic one with only positive coefficients. Okay, but in general, the philosophy is that we should have roughly this many solutions unless there's a good reason why we should not have that. On the other hand, it's not that hard to come up with systems like this, where we can fix half of the variables and then take the other half of the variables just as a permutation of the first half of the variables. In which case we would have almost p to the s over 2 variables. For instance, like if we have, well, one equation and all coefficients are the same. I guess that's the easiest example. Oh, half the coefficients are +1, half the coefficients are -1, something like that. So, well, this guy and that guy are compatible only if the number of variables is at least twice the degree. But if we have the number of variables bigger than twice the total degree, we would hope to get some kind of asymptotic formula like this. And I put in the C here in order to take care of the, well, local obstructions. So that's what we want to get. Can we get this? Well, this is the question again, reformulated. Well, we know it for linear equations. We know way more about linear equations. Linear equations are boring. We know it for quadratic equations as well, and yeah, have known for a while. And up to, yeah, very few years ago, 2-3 years ago, well, perhaps 4, this is all that was known, really. Now, thanks to the people on the top floor, we now have Vinogradov's mean value theorem in the general case. And that allows us to, well, that implies a positive answer here for systems where we have one linear equation, one quadratic, one cubic, and so on up to some degree. VMVT stands for Vinogradov mean value theorem. That's what that thing goes by in the literature. BDG is Bourgain, Demeter, Guth, who proved that. Well, Trevor Wooley proved the cubic case, and then they proved the whole thing. Well, we also know this for systems of one quadratic and one cubic equation. That's well, a result by Wooley, and that uses his proof of the cubic case of the Vinogradov mean value theorem. Well, one could say that this one is sort of slightly worse here, because in the upper ones, the 1 is really ceiling function of epsilon, and in this one, the 1 is ceiling function of 2/3. Luckily, the integers are discrete. And, well, for systems of cubic equations, things had been stuck at about 7 times the number of equations for quite a while, and then also quite recently, they did the work in, I think, 2013 or so. It was printed only last year. They got something like a positive answer to this, except it's not an asymptotic formula, it's only a lower bound. But that is pretty much, well, and the one is also ceiling function of very much, yeah, almost 1. So this is everything that's known before I start talking. And that's what I'll be telling you about in this talk, that I also know how to do this for 1 cubic and a bunch of quadratics, or 1 quadratic and a bunch of cubics. So we get, well, I mean, those are some of the simplest cases that are missing. I get other results for bigger systems of quadratics and cubics, you'll see that. So how does one go about proving results of this shape? I'll just try to give you a very quick overview of how 1 quadratic and 1 cubic goes. I'll also not talk about the main input that goes into there. I'll use that as a black box. So how do we do this? Well, let me define this kind of exponential sum. We have e of something stands for e to the 2i pi times something. So we have an exponential sum with a quadratic and a cubic equation. Then what is our number of solutions? Well, we've got the indicator function here on the quadratic equation. We've got the indicator function here on the cubic equation. If we multiply those two together, we get the indicator function on the whole system. And then we sum over all x's in our box. That gives us our number of solutions. Okay, but now we can rearrange the terms in here and write this just as the integral over several of these exponential sums, where we have the coefficients in the exponential sums. So this is the guy that we want to understand. Right, that's the guy we want to understand. And the idea is that we look at the integrand and we dissect the region of integration into a part where the integrand is large, and that's going to give the main term, and a part where the integrand is small, and that's going to give the error term. So that's what the dissection looks like. You essentially get the so-called major arcs. That's the error, well, that's the union of intervals that are close to fractions with small denominators. And yeah, then if you go through the analysis, you eventually end up at the expected main term. So we need to understand what happens on the minor arcs. We need to see if the error term is really smaller than this. Okay, what is a minor arcs? That's this kind of integral. Just plugged it in. Now, it's not, there's a fairly classical bound that shows that on the minor arcs we can bound one exponential sum by p to the 3/4. So we save a quarter there. Okay, we could do that all the time. Now we need to save 5, right? Because you remember our, well, up here, there. Our main term was 5 below the trivial bound. So we need to save 5, so we could sort of just take 20 exponential sums and save 5. But for that we need 20 exponential sums. I don't want to use 20 exponential sums. So let's do something cleverer. Let's take some of those into a mean value. Because if we talk to people on the top floor, or if we do it ourselves, then we can look at these mean values and we might get something close to square root cancellation there. And then we use this to salvage the last bit. And that is really the main input in that theorem for 1 quadratic and 1 cubic that really gets this mean value, which almost gives you square cancellation, except he loses by 1/6. But we win by a quarter. 1/4 is bigger than 1/6. Hey, so we win. Yeah, we have the main term, which is p to the s minus 5. We have the error term, lose by a 1/6, win by a quarter, win overall. Okay, so far so good. Questions up to this point? I guess I shouldn't ask, otherwise I won't prove my last theorem. Yeah. Right. So if we have a bigger system with more than 2 equations, what happens then? Well, we have our, so we've got our exponential sum again, but now we've got sort of several alphas because we've got several quadratic equations or several cubic equations. So the arguments of the exponential sums are going to be linear combinations of the alphas with the coefficients. So, well, we follow essentially the same method. We dissect our interval into major arcs and minor arcs. And on the major arcs, we get the expected main term. I mean, it goes by essentially standard methods. There's still some work to do there, but that's not where this kind of theorem fails. If this kind of theorem fails, it fails on the minor arcs. And on the minor arcs, well, we take out some mean value, and we estimate the other ones by the 3/4 bound that we had before. And now I took out this kind of mean value. The number of variables I have in here is twice the total degree. That's the critical point where we want to study our mean values. And okay, let's look at what this kind of guy looks like. And I'll just look at the easiest case, 2 quadratics, 1 cubic. Then we've got only 1 term in each product. And if we write down what this means in terms of Diophantine equations, okay, we've got 1 cubic, 2 quadratics. We've got 1/10th moment here. So we've got 10 variables here, yeah, 5 x's and 5 y's. We've got an absolute value, which means times complex conjugate, and complex conjugate gives you a minus. So we've got 5 pluses and 5 minuses here. Then we've got 4 variables in here, also 4 variables with pluses and minuses. So that's the system to which we want to count the number of solutions. Now, if you look hard at those bottom 2 equations, that's a matrix times a vector. If that matrix is non-singular, and we'll assume that it is, that's part of our non-singularity condition that I was saying at the beginning, then we can diagonalize that. Now that's easy. That last equation is pretty easy now. 1 quadratic in 4 variables, right, has p to the 2 plus epsilon solutions. Okay, that fixes the last 4 variables, so we end up needing to solve only the first 2 equations in only the first 10 variables. Okay, what's this? That's 1 cubic, 1 quadratic, 10 variables. Is essentially a 10th moment if you talk about mean values again. And that's what Trevor Wooley did in his theorem, and that's where he got 5 plus 1/6. So we put this together, get 7 plus 1/6. Okay, we started with 14 variables, total degree 7. We save almost 7, we lose by 1/6. So by the same argument as before, we get this kind of theorem. I just wrote down the general case when you have more quadratics than cubics. You get 4 times the number of quadratics. And this 20/3 should be read as 6 plus 2/3. And 2/3, well, I mean, you need essentially, yeah, the 2/3 is because you lose by a 1/6 and you win by a quarter. So the ratio between those two is 2/3. So that's going to be out in print this year. And, well, the same methods also work if you have more cubics than quadratics. Then you get 8 times the number of cubics and some correspondingly smaller number here. It also works for any kind of system with any kind of configuration of degrees. It just gets ugly to write down. But essentially, you end up decoupling your perhaps I shouldn't use that word. Well, you end up reducing your big system to subsystems where each degree occurs at most once, and those can be bounded by the Vinogradov arguments. So you get some theorem there depending on what the best mean values are on incomplete Vinogradov systems. If we have one cubic equation only, that's what we were just going through, then this guy is 6, which is 6 times 1 cubic, so we get essentially squared cancellation. Because we have, in that case, twice the total degree, 4 quadratics, 4 times the number of quadratics, plus 6 times our only cubic, plus 1. On the other hand, if 3 is bigger than 2, that 8 there is bigger than we would like it to be. We would like that 8 to be a 6. So let's see what we can do. There was this theorem at the beginning that I was talking about, that we essentially know how to do systems of cubics. So we should try to see whether we can use some of those methods in order to get systems of quadratics and cubics when we have lots of cubics, because it should behave in a similar way, right? Okay, so let's start again. Here's our number of solutions, here's our exponential sum, here's our change of variables, which, well, our matrix with the various alphas. Here's our mean value. We take S minus the total degree out, and I look at this wonderful, horrible mean value. You can believe me that this one contains 6R3 plus 4R2 exponential sums. I counted. Right. Don't look at it too much. It's big. But what we're going to do is we're going to try to bound this big, horrible mean value by one that's even bigger and even more horrible. Because the funny thing is that it works. So what we're going to do is, well, we've got this huge mean value, and perhaps I have enough time to write stuff at the blackboard. We've got our 3 cubic equations and our 2 quadratic equations. And this is essentially, we've got our 2 quadratic ones. Then we've got our 3 quadratic ones, our 2 eighth moments, another our 2 eighth moments at the end, and lots of fourth moments in the middle. Now this part is an R3 times R3 matrix, so we can diagonalize that. That's what I did down here. And now we're going to Cauchy-Schwarz, so we're going to take, do we have a color? Yellow, I like yellow. We're going to take the lowest R2 of the cubic equations here. We're going to take out essentially the part of the diagonal and a fourth moment of the 8 here. And then if we Cauchy-Schwarz the correct way, we get 1 quadratic and cubic mean value from the quadratic and cubic here. Or well, we don't get 1, we get our 2 of them, which is why we have our 2 there. And then we get some other system, which is twice as big and looks like this, where again the gray parts are 8th moments, and the non-gray parts are parts that used to be 8 moments but are now 4th moments. Okay, So we can bound J1 in terms of J2. Now we iterate that, bound it by J4, and iterate and iterate and iterate, and you can see where that goes. And if we do that very often, we iterate, say, m times, so we get the quadratic and cubic mean value by something that's almost 1, because we add up lots of powers of 2, or inverses of powers of 2, and we get some horrible big mean value to some small power. And this guy contains a certain number of cubics and a certain number of quadratics and a certain number of variables, which all fit together. But the funny thing is that we can't really bound the number of solutions to this huge, horrible system. And we get something that looks like squared cancellation. Yeah, essentially we throw away the number of the quadratic ones, because we don't care any longer. So we would expect something. We've got Rn, 6 Rn variables roughly. We get a degree, 3 Rn. And then we miss by something that's constant in n. So if we blow it up, we miss by a constant amount. So if we blow it up, we miss by an amount that relatively becomes really small. The bigger the system is, the smaller is our relative error. And then we take the whole thing to a really tiny power. So our absolute sort of relative error goes to 0. So this is what happens if we plug it into the formula. And you see 3R3 plus 2R2 plus the 1/6 that comes from Wooley's mean value. And then this guy, which goes to 0, which is essentially just a fat epsilon. Yeah, for every epsilon, you take your m big enough so that this guy is smaller than epsilon. OK, so we plug that into our formula from before. And that gives us this kind of theorem. So we get our number of expected solutions, provided the number of variables is bigger than 6r cubed. And this is 4 plus 2/3. So 6 times the number of cubics and 4 times the number of quadratics, and we're sort of off by 2/3 times the number of quadratics. And yeah, this works if the number of cubics is at least twice the number of quadratics. Why is that? Well, we have two reasons. One is here, this picture. This much is R3 minus R2. We need to fit, if these two 8th moments overlap, if I go back, perhaps let's not go back. If these two 8th moments overlap, then that's not a problem. You can still get the argument to work. If these 8th moments don't fit in, then that is a problem. So those are some of the technical reasons why we need at least twice the number of quadratics. OK, so if we combine that with the other one, we get pretty much squared cancellation. We miss by 2/3 times the smaller one if we're not in that critical range. That critical range, needs better ideas, which one can come up with, I suppose. But if the smaller one of these is 1, then this minimum is 1, so the floor function is 0. So in that case, we do get squared cancellation as we were hoping for. OK, and that's all I prepared.
Suppose you restrict yourself to the case of 1 cubic and 1 quadratic.
Yes.
But you don't ask that the quadratic is diagonal. Can you do anything better than Birch in that setting?
I have not thought about that, but perhaps we should. So yeah, I guess one could try to diagonalize it, and but then the cubic gets messed up. Let's think about this. We're here all terms, so yeah.
If you had, is there anything you can do for higher degrees? So you have like quadratics and cubics. If you say you had like a bunch of quadratics in one quartic, would it all break down?
Well, we would not get squared cancellation because we would need a good quartic and quadratic mean value. Because here in this Cauchy-Schwarz step, we get some quadratic and cubic mean value in there. And the reason why we get squared cancellation is because we would lose only by a sixth, which is less than a quarter. And a quarter is what we save on a cubic equation on the minor arcs. So if you had quartics, you would have to say, well, you would be allowed to lose by even less. And there is also just no quartic and quadratic mean value available at the time that is up to that. But you would still get a result. It would just not be squared cancellation. One thing that is relevant is that the miracle here, I said I was throwing the quadratic equations away. So this is a huge cubic system which I'm solving. And that cubic system, well, that miracle is particular to cubics as far as I am aware at the moment. So Jörg and Trevor have, of course, used some, have first had these ideas for their systems of cubics. And they say that it should be a very flexible method, and one should be able to do more with that. But it works for systems of cubics because we understand the, we understand them quite well. I don't know if I haven't gotten it to work for systems of cubics and quadratics, and for only quadratics we have perfect mean values anyway. So at the moment I'm not aware of any situation where this miracle applies that is interesting and not only systems of cubics. So quadratics and quintics would be something that would not work with this last method.
Yeah, so there's also a problem where you don't care about the asymptotic formula, but just about Hasse principle, say, and you might have to reduce the number of variables. Have you thought about that at all?
Well, I am essentially doing Hasse principles because, well, I mean, you mean lower bounds. So, yeah, well, we're just lucky in that the quadratic and cubic mean value works for entire exponential sums and not just smooth ones. But,
Okay.
yeah.
All right, but you don't know if you could reach the 2D plus 1 number of variables by if you only cared about the Hasse principle using some other maths.
There is no quadratic and cubic mean value perfect mean value available for any subset of variables at the moment. So you would need to prove that in order to get the full Hasse principle for that. So all these 2/3 by which we miss at the end, that's all because Trevor isn't perfect.